Hi, I'm Fred Coolidge, and we're going to talk about the t-test for independent groups, which is your Chapter 7, the t-test for independent groups. And just a reminder here is that this experimental design is the most powerful, and this statistical analysis is the perfect way of examining whether a treatment works for some group or not. So just as a reminder, we have an experimental group. We have a control group. This experimental group is going to get some treatment, and we have to make sure that it isn't just that they've been chosen for the experimental group, so we want to make sure that we treat the control group just the same. So we're going to have to come up with some sort of parallel treatment to see whether this really works beyond chance and beyond just, hey, you were chosen for the experimental group. So what we're going to do here is we're going to randomly assign, if we can, participants to each group. That means everybody has a chance to be in either group. And here's like participant 1 and participant K, the kth person, the last person in the group. And then each of them has some sort of score. So this would be the score of x1, x2, x3, x sub k for this group. And what we're going to do is get the parameter of interest in a t-test is the mean on this dependent variable, whatever we're measuring, to see if this treatment works. That's the dependent variable, also called the response variable. We do the same thing here. We don't have to have equal numbers of subjects, but it's nice if we do. And this is participant sub k, the last person in that group. And we should have at least 10 to 15 in each group, so we have sufficient power to see if this treatment works. So we're going to have a mean on this dependent variable for the experimental group, and we're going to have a mean on this dependent variable, same dependent variable, for this control group. Now remember too that what we're doing is we're testing. We don't want to see if the treatment just works for these two groups. So our null hypothesis is that the mean of everybody who would ever get this treatment, that's the population mean, mu on this dependent variable for the experimental group. And we'll say, you know, this equal sign really means is not different, that the mean of the dependent variable for the control group. And that's anybody that served in the control group. So we want to see, not just for this experiment, but we want to see, does this treatment work for anybody who would ever participate in an experiment? But we're going to use this sample, these two sample means, to estimate these two population means. Now, we're actually hoping the alternative is true, that the mean of this dependent variable for the experimental group is different than the mean for the dependent variable for the control group. And usually that's why we do the experiment, to see whether this new treatment actually works. If this response variable, let's say it's pain, a pain scale, and the pain is 10 is the maximum pain. Everybody's in pain that's assigned to these two groups. And 1 is absolute pain gone. I put pain gone here. Well, then what we're hoping here is that in the population, that this thing really works. If we get to reject the null hypothesis, we're hoping that the mean for the dependent variable for the experimental group is going to be less pain than this group that is essentially untreated, except they got chosen to be in our experiment. Okay, so what I wanted to focus on in this lecture is how do we test for significance? First of all, we got something interesting here. What you see in your books on page 438, on this side of the page it says two-tailed or non-directional. On the right side of the page, which I want you to ignore, it says one-tailed or directional. And they even ask this question on licensing exams for clinical psychologists. What makes a two-tailed or non-directional test? And that is the way you state the alternative hypothesis. Have you stated it in one direction? Did you state it this way? Actually, you said the mean, you're hoping the mean for this, because the pain goes down, mean for the experimental group is less on the dependent variable of pain than the control group. But that isn't the way we stated it. So let's go over that again. What makes it a two-tailed or non-directional test? You do by the way you state the alternative hypothesis. So notice there's two options here. This mean could be greater than this mean, or this mean could be less than this mean. That's what makes it a two-tailed or non-directional test. And as you read the book, especially in chapter 7, I say we're going to be non-directional kind of people. It's safer. It makes us more conservative, if you like. I always have suspicions when somebody uses a one-tailed directional test, but that's also in the book and we'll talk about it later. Okay, so now we're going to take these means, we're going to take these standard deviations, we're going to put it in that formula, and that formula, if you'll remember, for the t-test is this t-value equals the mean on the dependent variable for the experimental group, or the first group, minus the mean on the dependent variable for the control group, divided by a whole bunch of stuff. And actually over here are standard deviations, and over here for the two groups, and over here are the reciprocals of the number of subjects in each group. Now, you can see right here that the t-value is highly going to be a function of this numerator. That's one of it, one of the factors in making a t. But if the means are very close together, that is, HO seems to be true, these means are really close together, subtracting this number from this number, you'll only have chance differences. T is going to be small. So when we go to this two-tailed non-directional test, you'll see a t-distribution, and it looks very normal. This is a t-distribution. This is frequency. This is a low t-value. This is the t-distribution. And this is a very high t-value. So the mean of this t-distribution is going to be t equals 0.000. It's just convention that we put 3 zeros. So here's the t-value. That's the mean. And what this says is, what's its frequency? Well, that's the most likely occurring score by chance. Values out here, very unlikely by chance. Values out here, frequency, very unlikely by chance. And so what we have, if you'll read in chapter 7, is we have what is going to make us reject or retain, those are our two options, reject or retain this null hypothesis. It's going to be this t-value placed on this t-distribution, where we know that this is very likely due to chance. In fact, the most likely, by chance alone, would be a t-value of 0. And this is going to be a positive high t-value, and this is going to be a very strong negative t-value. So we'll run all our numbers from the experiment through here, pooling the standard deviations, multiplying by the reciprocals of n, dividing that into the difference between these two means, and we're going to get a derived t-value. We're going to derive this value. This value, these two values right here, are going to come from this page 438. Okay, so let's use our intuition. If HO's likely to be true and only chance operates, then this t-value is likely to be 0, because this difference between the means is so small that t is going to be highly a function of the difference between those two means. So our derived t-value will be close to 0. Only chance differences between the means. That means HO is likely to be true and we'll retain HO. What will we claim? That this new treatment doesn't work any better than a placebo. Okay, next, I'm going to erase all this so we have some more room. I'm going to erase this, and now we're going to test for significance. So, let's remember this. If we retain HO, then we're claiming that the treatment does not work any better than a placebo. We retain HO. And our significance level, we're going to say that's greater than 0.05, a greater than a 5% chance we could get that result by chance alone. So we're going to retain HO, and we will all, if we retain HO, we will always put P greater than 0.05. That means this is a non-significant difference. Our experiment did not reach significance, but what it really means, and specifically for those two means, is the non-significant difference means only chance differentiates those two. Whatever this treatment was, it didn't work any better than the placebo that we gave to the control. Non-significant. It'll always be P greater than 0.05. The only variation you'll see is sometimes you'll see in a journal article, it'll say P equals NS. And this will usually be lowercase ns in cursive in italics. What do you think that stands for? Of course, non-significant. It'll always, if you retain HO, it'll always be P greater than 0.05. Now, here's a trick question. When will it be P greater than 0.01? Good, never. If you retain HO, it'll always be P greater than 0.05. This is absurd. It'll never occur. You'll never see it. You might, the only alternative to P greater than 0.05, if they retain HO and they say there's a non-significant difference between the means, is you might see P equals NS, non-significant. When will I see, another trick question, but this is getting less tricky, when will we see 0.001? Good, never. It's always, if we retain HO, it's always going to be P greater than 0.05. Now, let's finally test for significance. So here's our T distribution. Here's the frequency. Remember, this is a family of T values, usually perfectly normally distributed. This is frequency. This is the most likely occurring score is T equals 0.000, which says there's virtually no differences between the means except chance. Now, what we're going to do is set up our critical values, and that's where this table comes into play on page 438. So, first we need degrees of freedom. You know, in the two-tailed or non-directional test, the degrees of freedom are going to be df equals n1 plus n2 minus 2. That's given to us. All we have to do is calculate it. How many people in group 1, how many people in group 2, subtract 2, and you've got the value of the degrees of freedom. So what I chose here for an example is 15 people in each group. 15 plus 15 is 30 minus 2. And we're in degrees of freedom, of that column, degrees of freedom, we're going to go to 28. Okay, now in your book, it'll say level of significance. Now the conventional level, I'm going to get high tech here. The conventional level of statistical significance is 0.05. We'll always search here first. And we see that our critical value is 2.048. And that's actually plus or minus. So here's what we're going to have. Our critical value, we're going to take from this table for degrees of freedom 28. We're always going here first. And we're going to put T equals 2.048. And right here, this is going to be the same exact value. T equals negative 2.048. If we get a T value, when we derive this T value, when we calculate this T value, if we get a value on this line scale that falls in this rejection region, we will reject HO. And if we get a value that's greater than 2.048, we'll reject HO, the null hypothesis. And if a value falls between here and here, we will retain HO. So let's try a value. We do this whole thing and we get 1.996. Now notice something too here. It's arbitrary which is first, which group is first. It does not matter. If this mean is less than this mean, you'll get a negative t. If this mean is greater than this mean, you'll get a positive t. So the value will come out exactly the same. It's only the sign, and the sign completely depends on whether this mean is greater than this mean or not. Okay, so we derived the t. Let's place it on this t distribution. Which t distribution was this? Oh, it was the distribution when the degrees of freedom equaled 28. Okay, 1.96. I'd say it's somewhere like here. T equals 1.996. What does that mean? We will retain HO. If we retain HO, which way does our P value go? We're going to say there's a non-significant difference between the means. The treatment didn't work any better than a simple placebo, and P is greater than 0.05. It's just too likely that chance differences could have caused this value. Let's try another value of t. 2.511. And again, I've made this mean greater than this mean. Doesn't matter. If this mean was less, this value still, divided out, would just be negative if this mean was less than this mean. So we got a value of 2.511. That's right here on this line scale, which means here's t equal 2.511. It means we get to reject the null hypothesis because our value exceeded 2.048. So now we can say this mean is greater than this mean. And the probability, by chance alone, that we're wrong is P less than 0.05. There is a significant difference. We found significance. But really what that significance means is there was a, I've got to write this better. There is our findings, we found significant, and what it really means is there's a significant difference between those two means. This one is significantly greater, and the probability we're wrong is 0.05. So, if we retain HO, it'll always be P greater than 0.05. It'll never be anything else. When will it be P greater than 0.01? Never. Always P greater than 0.05 or P equals NS. That means if there's a non-significant difference between the means, any difference we attribute to chance. Now, in the case of this bigger T, we found there's a significant difference because our derived value exceeded this value. And we know that there's only a 5% chance total by chance alone. There's only a 2.5% chance by chance alone a T value would fall in this range or in this range. This is 2.5%. So the total is 5%. And 5% is the standard level of statistical significance. I also noted in the book that what we have is the Greek letter, lowercase letter alpha, represents the conventional level of statistical significance, which is 0.05. There has to be less than a 5% chance. There has to be a less than a 5% probability that what we observed difference between the means were due to chance. And if it's less than 5%, then we can say there's a significant difference. P is less than 0.05. So in this case, we can say we reject HO because our derived value exceeded this critical value. And it's really a plus or minus, as you knew. We reject HO. We can say there's a significant difference. between the means and we can say it met the conventional level of statistical significance. So as soon as we see the less than sign, we know that we have significance, p less than 0.05. It means a significant difference between the means. We can reject the null hypothesis. Now, the exciting part is, can we say, we've said that this mean is greater than this mean, and the probability we're wrong, the probability by chance is less than 5%. So we have a significant difference. Can we say that the probability we're wrong is less than 0.01? Well, let's look at our critical value here. Plus or minus 2.763. So now it's a little further out, only a 1%, half of 1% in this corner. Here's our critical value, 2.763. Here's our critical value over here, negative 2.763. We have 2.511. Does 2.511, is it greater than 2.763? No. So we can't say p less than 0.01. In final review, if we retain HO, and our derived value does not exceed this critical value, 0.05, that's where we always start, then there's a non-significant difference between the means, and it's always p greater than 0.05. There'll be no variation. If we get to reject HO, and how do we get to reject HO? We go here first. The conventional level of statistical significance is alpha equals 0.05. And do you know how happy I was to move to Colorado Springs? And I got to see on bumper stickers on cars with alpha. I said, this has got to be the smartest city in the world. They drive around with a conventional level of significance on their bumpers. So, if we get to reject HO, if our value exceeds this one, then we can report significant difference between the means, and we put p less than 0.05. But our job is to report the lowest p level possible. So then we'll check it at 0.01. Can we say p less than 0.01? And can we say the very impressive p less than 0.001, that our results only have 1 in 1,000 chances of being due to chance? More than likely then, of course, the treatment works. But anything p less than 0.05, 0.01, less than 0.001, these are going to be our levels of significance. Remember, when we reject HO, they're significant. We'll start at 0.05 and then we'll check at 0.01 and 0.001. Thank you for your attention.